all right? And this is the VBS, all right? So the VBS is a blower in it. There might be, and there's going to be a mist and grease filter is typically going to be before the blower, okay, for mist and grease filter. I'm not showing you the spirit, not drawing this out very well, but there's a mist and grease filter before the blower, and then the blower is blowing into the bottom of the unit and upflow. That's kind of a standard VBS design. Many times this will be on a skid, okay? Customer may order it on a skid. All right, that skid is actually a fairly costly thing for the unit, right? We you know, it's and really the skid is only beneficial to make sure that it all mounts up here, and then it's kind of it's almost like a shipping skid, right? So the contractor can kind of take the thing and drop it all on site, but it costs us a lot of money to get that skid made because it's all custom done. So we prefer not to include a skid and just have the contractor bolt down the vessel and the blower separately. And they're usually okay with that. All right, so we have the unit, the air comes in the mist and grease filter. Now, and then through the blower. The reason we put the mist and grease filter before the blower is we're trying to keep all that mist and grease from getting in the blower as well. Just as that grease can get in here and mess things up, the grease can also get into the blower. And these blowers spin at very high speeds, and any kind of collection of grease on the blower can muck things up a lot and cause imbalance and all sorts of other things. So we like to get the air clean coming into the unit. Then the air goes up and it goes through the unit. Now, occasionally we have a need for a VBS that has a downflow to it, where the air is coming in the top and going out the bottom, okay? And that is typically done let's look at that. Okay, this is a VBS and a downflow, and we typically use a VBS and a downflow when we're using an emergency chlorine scrubber. Okay, now emergency chlorine scrubber, very often we have different designs of emergency chlorine scrubber, but when we have an emergency chlorine scrubber in a VBS design, so it's a VBS but we've assigned it to become an emergency chlorine scrubber, the chlorine gas will come in the top, and then it'll start consuming the adsorbent media. Now keep in mind, with our adsorbent media, the adsorbent media gets used in a band, starting from the inlet of the air, the inlet side of the media, to the outlet. So if you've got an emergency chlorine scrubber and it's designed to capture up to 2,000 pounds of chlorine, but let's say they only have a 100-pound release, what that allows us to do is work with the customer to just remove a top portion of this used up media, all right, and replace it with new media there. So that's why we work with a downflow for chlorine scrubbers. It also allows us to have the blower in the purified air. So this is chlorine coming out here, and this is just plain air coming out here, and so it allows the blower to stay out of the chlorine. Chlorine's very, very corrosive and such, and so you're better off to have the blower not in that kind of environment. Emergency chlorine scrubber also doesn't need a mist and grease filter because it only runs in the case of an emergency, where a mist and grease filter is meant for a unit which is for odor control, it's sewage treatment, there's nastiness in the air there, and it's running 24/7 all the time, right? So we don't need a mist and grease filter when we're talking about emergency gas scrubber. So that is one, when we make an emergency gas scrubber in a VBS design, that's why we have it in a downflow design. So the question is what are the advantages of a VBS? Well, let's not talk about advantages yet, because I'm gonna talk about the other system designs, and then we'll talk about advantages and disadvantages once you see the other designs. I don't want to get ahead of myself just yet. So that's the VBS. All right, now we'll talk about a special case of a VBS, which is called a dual bed VBS. So when it comes to VBS design, basically for a small airflow, you use a small round tank. You know, they start like a drum scrapper, there's a small round tank. And then as you need more airflow and more adsorbent media, then you start making the tank bigger and bigger and bigger and bigger, okay? Well, at the point where the tank gets to be more than 8 feet in diameter, it starts to get very expensive to ship these tanks, okay? Because you have to get special permits and they have to be put on special trucks and things like that. And so, you know, 8 feet in diameter is a special number, okay? That means anything kind of under 8 feet, we can ship without a permit, okay? But then when it comes to 12 feet, if you get up to a 12-foot tank, that's extra special, okay? Actually, anything from 8 to 12 requires special permits and things. You can even do a tank that's diameter up to 14 feet in diameter, but it's super extra special. Like the shipping is more expensive than the vessel itself. Okay, so so let's take a look at this and say, all right, well, we've got a 12-foot tank. How do we determine what the airflow is on a 12-foot tank? So we're gonna take a look at design already, and so this is our VBS unit. The air is coming in over here. All right. We're not going to worry about the blower at the moment. So we've got this media bed. So let's calculate the maximum airflow for one of these units. So for odor control design, the rate of the air going through this adsorbent media is typically 50 feet per minute. Okay, so that means the velocity of the air going through that media is typically 50 feet per minute. This is a very conservative number, and typically most of the consulting engineers out there are expecting 50 feet per minute here, but we know that our systems can actually perform fairly well at even higher numbers, okay? So, but for odor control, let's call this 50 feet per minute is the odor control standard. Okay, is that getting on there?
Yeah, it's probably moving a little bit.
75 feet per minute is kind of the range that we can go up to for odor control. We'll call that odor control possible. Okay. So especially if we have a very low level of odor, possibly, then we can kind of push the design up to 75 feet per minute. And then for protecting electronics, we can go up to 100 feet per minute. Okay? 100 feet per minute protecting electronics. So now why is it different for protecting electronics? Because when you're protecting electronics, the amount of contaminant coming into the system is far, far lower than an odor control system, all right? You're talking about 1/2 of a part per million coming into a system for protecting electronics that we need to get down to like 2 parts per billion or something like that. Whereas an odor control system, you're very often talking about 5 parts per million, 10 parts per million, something like that. So this means that we can't rush the air through too quickly because it needs some time inside the bed in order to be captured. Okay, so based on this 50 feet per minute, let's take a look at what our maximum airflow can be. So we've got our 12-foot diameter. So we need to determine the area of our tank, the cross-sectional area of our tank there. So somebody give me the area using pi r squared of a 12-foot tank. R being 6, which is half the diameter.
About 113.
113. Okay. So that means a 12-foot tank has 113 square feet of area. Is everybody following that? That the round portion here has 113 square feet. So using 113 square feet at 50 feet per minute, somebody multiply that 50 feet per minute, because this is the velocity through the area, and this is the area. So if we multiply those together, we'll get the total air volume, 113 times 50.
So area times feet per minute?
Yeah,
So 5,600.
5,600. Okay, so that means a 12-foot tank at 50 feet per minute has an airflow. You said 5,600?
Yes.
5,600 cubic feet per minute, okay? So we've converted velocity, or the speed of the air through the adsorbent media and the known area of the tank, and we've converted it to now basically the airflow of the system, okay? So what do you do if you need 11,000 CFM? You need another tank, okay? Wow, that's twice it. What happens if you need 7,000 CFM? You need another tank. So it gets to be problematic. Well, what happens when you need another tank? Well, you got this tank, now you need twice as much space, now you need duct connecting it to make sure that it's all going through, and it gets kind of complicated as far as that goes. So somebody came up with a bright idea of saying, well, let's put 2 media beds in one VBS and try to make that work. So this is what they came up with, right? We've got the same 12-foot tank. We've got a media bed here. We've got a media bed here. We've got an inlet here in the center, okay? And what we do is now you've got these 2 media beds, and what they'll do is they'll build a chimney here, actually, basically. That doesn't go all the way to the ground. That goes through, this is an internal chimney. Hey. And I'm giving a presentation at the moment. Okay, sounds good. Bye. So what happens is half of the air will go down and percolate down through the carbon, or the adsorbent media is in here, travel over, go up to this chimney, and exhaust out. So this won't have any media there, or here, and then exhaust out the chimney here, okay? And then half of the air will go up through here and travel out this chimney, okay? So you can see it's kind of a complex design, and let's talk about some of the deficiencies in this design. The first one is, how do you service this carbon bed down here, right? This is kind of a mess. You could put a manway in it here, and people could climb in here to get into the carbon. A lot of times what they'll do is they'll make this platform here removable, so that you can go and you can vacuum out the carbon through the top and take this carbon out, and then you move the gratings to the side, and somebody climbs down here and goes down to this carbon and vacuums it out. it's a mess. And generally, while engineers might kind of like this system because it solves a footprint problem is what it does, right? It also solves a cost problem now because you've taken almost this same vessel and you've doubled the airflow in it now. And so it helps reduce your costs quite a bit. But the reality is from a performance standpoint, customers hate this. And in general, we hate it as well because everybody and their brother can build this thing. Any fiberglass company out there that can build this and sell it. And we don't have any real advantage over anybody else in that. Let me show you another issue that comes with it too. So keep in mind that this air is racing through this manway here. You got 12,000, so now we've doubled our area, right? Because we got 2 beds. So now we've got 226 square feet of bed area. So we're able to do 11,200 CFM in there, okay?
Would you have to change the speed, would the 50 FPM still be 50 FPM going in?
It's still going, it's 50 FPM going through each of the carbon beds. So it's very high coming in here, but then it splits and half of it goes through here at 50 feet per minute and half of it goes through here at 50 feet per minute. Okay, so it's not the velocity coming into the tank, but the actual velocity through the carbon. Okay, so we're now at 11,200 CFM. This air is racing through. I did the calculation one time. It's coming in at like 50 miles per hour. Okay, we think of it in feet per minute, but it's something like 50 miles per hour. So stick your head out the window of a car going 50 miles per hour. You're getting that, right? So this air is coming through. A lot of times what we see is because the fiberglass guys are trying to make this vessel as short as possible, they'll have the inlet right here just above the carbon level. So what happens is the air comes in here, and just like a sand dune, just like the wind will blow a sand dune eventually, what happens is all the carbon ends up getting pushed up over here, and you end up having problems there. Well, what happens when all the carbon gets pushed up there? Well, then all the air starts going through the shallow part over here, and hardly any of it goes through the deep part. Then you get more air going through this bed than you have going through that bed, and everything gets all completely whacked out of balance here. You open up one of these units and there's a big slope of carbon on the bottom, and if you would have measured the airflow here, you'd get some kind of real high airflow here. Like instead of half of it, you'd probably get like 7,000 CFM coming out of this one. You get about 4,000 coming out of this one. So a lot of times engineers, in order to try to adjust that, will make you put an airflow damper here to control the airflow, so you can adjust it and get it. But by the time this carbon's all blown up against the wall there, all you're doing is kind of covering up problems with that. So it's a real lousy design. We do a few of these a year. We chased a project and somehow picked it up. But there's 4 or 5 guys out there that can build it, and it's not the type of unit that our sales guys like to sell because there's just not a whole lot for us to do, and it's problematic design. So, because of these designs, there's been another unit that has come out of the odor control design work, which is, so one thing I'll say, let me back up and say, we kind of say the VBS is the big brother of the drum scrubber, right? Drum scrubber's a little baby. VBS, sure, we can make some little babies, but we can also make some really big VBSs, okay? Well, the radial flow unit replaces the VBS. Let's just say it replaces the dual bed VBS, okay? Because the regular VBS still works well. This is a good unit here. There's nothing sexy about it, but it's a good unit. It's just the dual bed is problematic. And so the radial flow replaces the dual bed. Before we get into radial flow though, let's talk about the advantages of our vertical flow, okay? So one of the nice parts about a vertical flow is when you're using any type of adsorbent, when you put that adsorbent into the system, it's going to settle, all right? In the first few weeks that you fill the adsorbent, it's just like anything, like sand or anything like that. It's all made of particles, and those particles are going to kind of shake around a little bit, and they're going to settle just a little bit. Well, when it comes to a VBS design, if it's at this level and it settles down 1 inch lower than that level, it's not a problem, right? It's not a problem for us. There are other designs where that settling does cause a problem. So this unit is basically what we would say kind of self-sealing, in that the air is forced to go up through the adsorbent media. There's no other way for the air to get out of the unit. It has to go through the adsorbent media, okay? We're going to talk about horizontal flows in just a minute. And the horizontal flows have some real benefit, but one drawback is that there's the potential for the air to bypass around the adsorbent media, and it's very, very important that we understand that. So we'll talk about that more. But so this is a safe, simple design is basically what we say. There's not much wrong that can go with this.
Do we just make the VBS in 8-foot or 12-foot increments?
No, so the VBS can be made in 2, 3, 4, 5, 6, 7, 8, 10, up to 12-foot increments, basically. You're just not going to see a lot in our shop because we just don't sell them much.
When it's smaller.
Those are all VBS units. Let me just say, the two right above Rich's head are VBS units there. The one in the bottom in the middle, that's a radial flow. We'll talk about that in a minute. The two on the right hand, the two pictures on the right hand side, those are also VBSs. The one on the bottom right is actually 2 VBS tanks attached to one blower. Some engineer's idea of having a backup. The one in the top center is a monstrosity, which we won't even really talk about. It's an ugly design that I don't want anybody ever thinking that we could do.
Should I go ahead and take a picture down?
Anthony and I personally spent a lot of time on that site.
Do not sell this.
That's as a reminder.
That's-
Leave it up there as a reminder.
That's what?
That's
King Street,
Not
though.
Interday.
Anthony spent a lot of time personally at that site. That unit is installed in the parking lot of Reliance Field. No, what is it?
That's the, I think it's
Seattle's-
CenturyLink Stadium. is what it is
CenturyLink
now.
Stadium in Seattle. It's literally in a hole in the ground at the stadium.
Stadium parking lot.
There, yeah. Yeah, so, but that's a monstrosity. That's basically, what that is a dual bed unit turned on its side. So let's take a really lousy design and make it even worse. Right? That's what that is. It's a dual bed unit on its side. So, yeah. That was an experiment gone awry.
That's a round tank manufacturer thinking he's an odor control guy.
Yeah, that's correct. That's correct. And Rich brings up a very good point that I should mention. So that's the difference between, so we have two types of competitors. We have guys that sell activated carbon. So there's companies like, used to be Calgon, Norit Carbons, Continental Carbon. These are all guys that sell activated carbon, and they know all about activated carbon, and they got like 25,000 different types of activated carbon, okay, for all sorts of special applications. And they're going to basically help you select the one activated carbon that's going to do best for your application, okay? Lots of purposes for that. They use activated carbon to purify liquors. They use it to take colors out of things. They do air purification. They do all sorts of things with activated carbons. These guys know activated carbons. But if they were to sell an odor control system to somebody, they would go to some fiberglass manufacturer and they'd say, make me a round tank that I can put my carbon in, right? And they would buy that round tank from somebody and sell their carbon with it. Okay, so that's lots and lots of systems that are sold out there by these carbon companies for it. Our other type of competitor is the fiberglass company. And this is some guy that makes fiberglass, and he says, well, gosh, I've been making these fiberglass tanks for these carbon companies. Why don't I just start selling them myself as a whole system? And then I'll just buy carbon from some other guy and do it. So these fiberglass guys get into the odor control industry, and they make a beautiful fiberglass tank, really super nice, and then they go get some activated carbon from somebody that they buy and they put it in there, and that's what they call an odor control system. Pure Air is an odor control company, or we're an air purification company. Are we experts at fiberglass? Nope. Are we experts at figuring out the isotherm of coconut shell activated carbon? Nope. Okay, but do we know airflow? Yes. Do we know different types of absorbents? Do we know systems design? Absolutely. And we're able to put that all together. So, you know, we have a lot of customers that think that a fiberglass system, that odor control system has to be a round tank. And then we ask them and we say, well, you're putting this in a square room. Why do you want a round tank? And they go, because odor control systems have to be round. Say, really, where is that? I didn't see that in the handbook. Where's that in the odor control handbook? And then they start asking why. Why is it round? Why is it round? Well, it's because that's the way fiberglass guys like to make stuff. Because they get fiberglass companies will have a big spool made, basically, and they'll just turn this spool and spray it with fiberglass and turn it into a round tank. Okay, so that's the cheapest way for them to make a tank. And a round tank has some nice structural conditions and such, but the reality is nothing says it has to be round. And if you're going to put, you know, most rooms are not round. If you're going to put something into a room, usually you want it to kind of match the size of the room.